Hey everyone, welcome to the second video of this three-part series. In this video, we're going to go over the starter code. And once we go over the starter code and the different files that are given to you, as well as the actual classes you're going to write, which is MCryptFile, then we will go to the suggested implementation order that I posted on Ed. Before we go on, I want to suggest that you spend like an hour just going through the starter code yourself. Remember, this class is hopefully going to give you some confidence in going through a big code base. That's an important skill that you might need in the future for future CS classes or for research or for internships. So spend like an hour by yourself just going through the starter code, and then come back to the video and we can go through the starter code together. Okay, so assuming that you've done that, let's talk about the starter code. First is the not the MCryptFile, the CryptFile class. Okay, so this is the CryptFile class. You don't have to worry too much about the implementation of it. Just be aware of what functions are part of the CryptFile class. The CryptFile class is a superclass of the MCryptFile class. So you're implementing the MCryptFile class, and the MCryptFile class is a subclass of CryptFile. Okay, so what does that mean? That means that any method that is in CryptFile, for example, align p read, align p write, any method is also available in MCryptFile. So inside MCryptFile, you will definitely be using the functions like align p read, align p write, or file size. All right, so just be aware that inside MCryptFile, you also have access to these functions, and you should call them. For that reason, you don't have to worry about any file reading to do. Right? Like for file reading, you don't have to open up some IO stream. You don't have to, you don't have to check if the file exists. All you have to do is just, once your MCrypt file is created, you can assume that the file is already initialized, and you just have to call align p read and align p write. All right, so that is the CryptFile class. Crypto.hh is scary, so don't look too deep into this. You don't need to know anything inside this class. Let's now go to test.cc is the test cases that you're going to use. So we'll take a look at that last. Util.hh is, well, it just has a file, unique FD file descriptor. You don't have to use this at all. This is used in CryptFile.hh. VM.hh is the most important one because it defines some of the important classes that you need in your MCrypt file. So first is this class called VM region. VM region represents a region of virtual memory. Okay, now remember, virtual memory, you're not actually explicitly allocating like an actual physical array that stores the virtual memory. Okay, this is just what the programmer who is using your MCryptFile class imagines that memory looks like. Okay, but in reality, the pages inside VM region are mapped to physical pages once they are brought in. It's like the example that we did before, where the green array that we showed is not actually like an actual array until you allocate physical pages for each virtual page. The constructor of the VM region is over here, and it has the parameter for n bytes. So how big do you want your VM region to be, as well as this function. You should recognize this from your project too, where you can pass in a function pointer. This is the same as here. This is the page fault handler, right? Remember from the previous video that the page fault handler is called when you allocate a region you allocate a VM region, but then you try to access a page that is not mapped in virtual memory. So if it will generate a page fault if you access any of its pages. Okay, and then the page fault, when it generates a page fault, it will call your handler function. It will give the input to the handler function is the faulting address, and you can use that address to figure out which page is faulting. And then kind of like the same sequence that we did before, you are able to go through and update the page map, update the supplemental page map, and the bring physical memory, allocate a physical page. Okay, so that's the handler there. So when you initialize your VM region, you will have to pass in a handler. So you have to write your own function to pass in. It's very similar to project 2, where you had to pass in a start function. The VM region, as I drew in the diagram, there is a base and a size, get base, base size. These are helpful to implement your MCryptFile class, which also has a get base and get size. Okay, now there are these two functions. They are static functions. Okay, and then the reason that they're static functions is because when you call map and unmap, they are updating a shared page table that is shared among all the MCryptFile instances. Okay, so these don't modify member variables inside a VM region. These modify the shared page table. That's why these are static functions. For the map class, you basically just say, kind of like in our table, you pass in the V page, you pass in the P page, and you pass in some protection. And then in the unmap, you just pass in a V page to unmap it from the table. Okay, so map adds it to the table, unmap removes it from the table. If the V page already exists, then if you call map, then that entry is just replaced by this new entry you put. You don't have to worry about this private section. Although what is interesting about the private section is you might see how the page table is implemented here. This is an unordered map. So yeah, when you implement your own supplemental page table, you might, you'd be using a unordered map. I would say though that the way that this page map is implemented is a little bit more complicated than you need your supplemental page map to be done. Like, sure, you definitely want the V page as the key, but instead of storing like a pointer, a heap allocated pointer to something, there's a simpler way to do it. So yeah, use this as inspiration for what your supplemental page table should look like, but you don't need, it won't be as complicated as what the starter code is implementing. Okay, so that is the VM region. Now, I used these already below, but P page and V page, the ones that we had in our diagram, they're just char stars, they're addresses. Okay, but nevertheless, when you write your code, you should use these types to make it super clear that you're dealing with a virtual page or a physical page, because it's very easy to confuse them if you just store them as char stars. There's also this prot type, which it's secretly an int, but it has 3 values: prot none, prot read, and prot read or prot write. You'll use these in the last step, which is in the 3rd video that I'll go over. All right, so that's VM region. Physmem here it represents physical memory. It has a fixed number of physical pages, and these are you will create one instance of Physmem and you'll share it among every MCryptFile instances. So remember in our diagram, we had one Physmem table, and that is shared among all of the MCryptFiles. So you create one Physmem, the memory for Physmem is shared among every MCryptFile. And that's very important. So make sure that the Physmem you declare is static. It's shared among all MCryptFile classes. All right, so what is in Physmem? The most important functions are page alloc and page free. Page alloc allocates a page. It returns a physical page. Okay, and then you can use that physical page to, put it into the page table. And then you can also read from the file using align p read. Okay, this will return null pointer if there are no more pages, right? Because there's a fixed number of pages. When you create Physmem, you pass in a number that represents how many pages are created. When you run out of pages, this will return null pointer. For now, you don't have to. You can just assume that it will never return null pointer. Okay, in the next project, in project 6, you will deal with the fact that if it returns a null pointer, so if there are no more pages, you have to evict a page and then bring a new page into that spot. Okay, but for now, you can just assume it will not be null pointer. And don't forget, anytime you allocate a page, when you don't need that page anymore, you should free the page. So whenever you call a map, you make sure you free the page. Okay, and then there's also the pool base in case you ever need to access the base of physical memory. The physical memory region that is declared is contiguous. So you can use that to determine like where all the different physical pages are. All right, that is the Physmem class. Yeah, you don't have to worry about any of the private data here. Now let's go to your MCryptFile. So in MCryptFile.hh, now just like the header files for the other projects, you put your private variables here. Okay, and all the public members that you're declaring that you'll be implementing are up here. Okay, now there are 2 of these functions that, because they're super short, the starter code just decides to put them in the .h file. Okay, so make sure you implement these. You shouldn't figure out how to implement these. These are based on the VM region. So once you initialize the VM region, you should be able to implement these. Okay, now let's go to the MCryptFile. So I will go through the suggested implementation order. And then while we go through that, I'll come back to the starter code to give you some hints about what you would implement here. So let's look at the different functions. So this suggested implementation order is first you review section 6, problem 2. So what is section 6, problem 2? Let me bring it up. Section 6, problem 2. That is this problem about the virtual memory classes. So definitely review this because Jerry has written a bunch of examples on how to declare a VM region, how to declare a FISMEM, and how you use those two classes. Okay, so make sure you take a look at this example. This example is super important. And look at the solutions to understand what physical pages and virtual pages are doing in this example. All right. So first review that, then you can declare and initialize your static and member variables that keep track of memory. In our diagram that we drew in the previous video, you saw a bunch of different data structures that are used. There's a VM region for every single MCryptFile. And then there is a shared FISMEM region. There's also a shared supplemental page table. And then there's a secret page map. You don't have to implement the page map because VM region already implements that. Okay, so there's 3 different things. The VM region, each MCryptFile one class has one, a shared FISMEM, and a shared supplemental page table. Okay, so remember to, when you declare them, make sure you declare them in the .h file here. Now, here is something that's a little tricky, which is that in the project, it says that there's a part here that says, here, create a single FISMEM object and share it across all MCryptFiles. Don't create this object until the first time an MCryptFile is mapped. So the FISMEM object should not be created until map is called, the first time map is ever called. Similarly, for the VM region, right? We said when we went over the example for the VM region, when you initially create the MCryptFile, the VM region is not constructed yet. It's only when you call the map function where you're given this size. And it's only when you're given this size do you know how big your VM region should be, right? So you can't construct your VM region until you call map. For that reason, just declaring VM region, like VM and FISMEM, just declaring this won't work because remember that for member variables, if you declare them directly here, then you have to initialize them in your constructor. You'd have to go to your constructor and you'd have to, here you would have to call the constructor of VM. You have to pass in the size of the virtual memory region and you have to pass in the page fault handler. But here you don't know what the size is. You only know what the size is until when map is called. Right. So remember, you cannot construct your VM, your virtual memory region and your physical memory immediately in the constructor. Okay. Unfortunately, when if you declare like this, you can't set an object to null if you declare like this. So instead, what I recommend is you have 2 options. When I think this project was originally developed, they were hoping that you would use this thing called std optional. Okay, what this means is it's VM region, but it could also be null. Like you can have it's either empty or it has a VM region. Now this class is kind of hard to use. I'll be honest. I tried to figure out how to use it and it's very tricky. So there is a alternative suggestion here. Yeah, so I mentioned here, construct upon first call to map. So the alternative suggestion is to declare them as pointers that you initialize to null pointer. Okay, because the nice thing about pointers is pointers can be null pointer, right? If you have a pointer to a FISMEM object, that pointer can initially just be null pointer, and you only construct the FISMEM afterwards. So after the call to map, do you then construct the FISMEM and then store the pointer as your member or static variable? Okay, so for that reason, I recommend that you do a pointer. Oops. Something like this. Yeah, you might, I'm not sure, maybe in MCryptFile.h, you might need to include a unique pointer. Okay. Yeah, and don't forget, you also need your auxiliary supplemental. I'll let you figure out how to represent your supplemental page table. Right? I kind of hinted that you might want to use an unordered map, but what exactly is your key and value pairs? Okay, you might need to declare like some extra structs to store all the relevant information you need to store for your supplemental page table. Don't forget, this is static because it needs to be shared among all instances of MCryptFile, right? We drew one supplemental page table for the entire MCryptFile class. All right, so that's it for the member variables. Make sure you implement. Actually, don't implement these yet. Implement those later. Let's take a look at let's continue with the implementation order. Here we construct it using std make unique. Okay, so there we go. Initially, these two, the virtual memory and the physical memory, should be initialized to null pointer, right? So how do you initialize a member variable to be null pointer? You do that by doing it in the constructor in the initializer list here. You would say something like VM null pointer. While for physical memory, for this physmem, you do want to initialize to null pointer, but you don't do it in the constructor, right? Because it's static. How do you initialize a static variable? You've done it in project 2. So I'll let you just go back to project 2 and check out that syntax. The syntax is very similar. You initialize it up here to null pointer. Okay, yeah, check out your project 2 start. Project 2 code, you should have initialized a bunch of static variables like your ready queue and your current thread, right? Just initialize them up here. All right, then, yeah, also don't forget to initialize your supplemental page table. Now, the supplemental page table doesn't have to be a unique pointer. And the reason for that is you can just start the supplemental page table, just create it and make it empty, right? There's no rule that you can only create the supplemental page table once you call map. So just create it. You don't need a pointer. All right. So is that it? Okay, that's mostly it for the constructor. Last thing about the constructor is this thing. This is called the delegating constructor. And what it does is it just calls the constructor of CryptFile. Because remember, MCryptFile is a subclass of CryptFile. And the CryptFile constructor handles the key and the path. So you don't have to worry about this, the CryptFile, the key, and the path. You don't have to open any files. This call to the CryptFile constructor will handle it for you. For the initializer list, you just put the remaining members you want to initialize afterwards, like in a comma separated list. All right, so we have done the constructor. Now let's talk about the first call to map. Okay, so in the first call to map, you are given a min size. This is the minimum size of the VM region. Okay, now you might, if the min size that is passed is too small, you might need to declare a larger size so the entire file fits in. Okay, so the actual VM region size that you declare, as you see here, is going to be the larger of min size, the parameter, and the original file size. Okay, you can find the original file size, go to the CryptFile class, and there is a function that can help you determine what the file size is. Okay. So inside map is where you need to initialize your physmem and your VM region, right? You don't remember in the map function, you're not doing any page fault handling yet. Here, all you're doing is setting up your physmem and your VM region. Since you've already declared the physmem and the VM region pointers before, you should have access to those 2 pointers. Now, upon the first call to map, that is when you can set the VM region and the physmem by constructing a new VM region or a physmem. Okay, but you only construct it if the pointer is initially null. So something like if the VM pointer is null, then you can construct a VM. Okay, and I recommend that you use this function called make unique. I recommend that you Google it, learn more about it. This is a very important standard library function you want to use. The documentation is a little long, but you can check out the examples to see how you use. Okay, maybe the examples here aren't great. You maybe want to check out like documentation like here, and it shows you some examples on how you would use unique pointer here. Okay, but the idea of make unique is make unique is a template function. You pass in the type that you want to construct a pointer to. So for VM is a VM region pointer. So we want to construct a VM region. And in the parameters, you pass in the parameters to the constructor. Okay, so you pass in the parameters, which I believe is the size, and then the okay. Now this is equivalent. This is equivalent to something like, create VM region size and page handler, then create a unique pointer that points to that. Okay, so make unique basically does these two steps, and it returns that unique pointer. Okay, the reason why we have this function to do it for us is because unique pointers can't be copied. So it's a very big pain to have to construct a VM region, create a pointer, and then copy that pointer over. Okay, you have to do like a bunch of STD moves. So instead, there's this function that does it for you. Okay, same for physical memory. But remember, physical memory, you only create it once. Okay, so you definitely will need to check if the physical memory pointer is null. Now, when you initialize this, the size we just mentioned, you can figure that out by using the min size and the size of the file. But the page fault handler is a little harder to create. So the page fault handler, you have to pass in a function. And what I recommend that you do is you should check out, as I already mentioned, you should check out Jerry's example. This is actually example 3. Did I say check out example 3? Okay, I should move the problem 3 up here. Yeah, you want to check out problem 3 because problem 3 tells you exactly what your page fault, like what the syntax of the page fault handler is. So here you can see that we're initializing the virtual memory. You pass in the size, and you also pass in the page fault handler. Okay, this is a Lambda function. And this page fault handler is calling a function that you write called fault. Okay, so this is the actual body of the page fault handler. For step 1, leave it blank for now, because you can just add it in later. For now, just declare this function, and then inside of your VM constructor, you can just construct it. You can just construct a Lambda that calls your fault handler. Make sure you capture this. The reason you want to capture this is so that fault here can be called. Fault is a member function, right? We're declaring it inside of struct, so fault is a member function. And the reason we want to make fault a member function is so that you can access the member variables inside of your struct. So in our problem, when you declare your fault handler, let's say, when you declare a fault handler like this, you want to make this oops, they also covered those numbers. You want to make this a member function, because if you want to access your virtual memory region or all the other member variables or static variables, you need to make it a member function. Okay, so make sure you capture this and simply just use this syntax, like use the syntax that Jerry tells you to. Okay, that will help you construct your page fault handler. For now, let me just write the page fault handler out. Okay, so declare one and then use that syntax and pass in the page fault handler. All right, that should solve the first step. Yeah, leave its body empty for now. Then I have to say to implement map base and map size. So which is here, right? Map base and map size are related to the VM region. So once you construct the VM region here, then you're able to call that. Okay, be sure to check if it is an error to call this before calling map or after calling unmap. So if the VM region is not created yet, you can just either throw an error or return null pointer, up to you. Okay. So once you're done with this, when you run .test read, so make everything and then run the test case read, you'll see that the file is successfully mapped. Okay, before you do anything, like if you just run the starter code, this test will crash immediately. But once you have successfully implemented this first step, you'll see that their first 3 lines, you'll see successfully allocated the file successfully allocated some number of some VM region, but then it will hang. And the reason it hangs is because the test case tries to do a lot of reads. Let me pull up the test cases. The test case does a lot of reads. Read test here. Okay, so yeah, you create the test. Yeah, once you have implemented the first step, you will see like the first couple of lines, and then it will hang. It won't crash, it will hang, because when you start trying to read, that will generate a bunch of page faults, right? Because the page's reading is not in physical memory, but you have a page fault handler that is called, but your page fault handler doesn't do anything. So these page faults just repeatedly happen again and again. Okay, now that is the first step. Once if it starts hanging, then you know that you've done it correctly. Okay, then in step 2, that's where you actually implement the page fault handler. That's where you fill in the body of the page fault handler. Okay, and we went over the steps on how do you handle a page fault, but Jerry also gives you the steps here in problem 3. Okay, yeah, Jerry actually just tells you step by step how to do it. So yeah, just take a look at, for example, if you want to mask away the lower 12 bits, that's taking the last 3 digits of the hex address and making them zeros, right? That's what we did in our example. That is the same as masking the lower 12 bits, which you do using this code. Okay. Yeah, we went over these 4 steps in the video. Here's just another reminder of those 4 steps. Okay. Yeah, so you just implement the page fault handler. When you call map, so when you call map here, determine protections, to call map, for now, just set everything to prot read or prot write, because we'll figure out the protections later. But for now, if you set prot read, prot write, then you won't get any issues if you try writing or reading. Okay, once you're done with this, you should get in the test case, everything will be successful. Like you'll see everything printed. But what happens is that when you go out of scope, when MCryptFile goes out of scope, the destructor is called, but we haven't implemented the destructor. So we haven't unmapped everything. So you should see some error about how there are pages that are not mapped. There should be some assertion error. That's fine. If you're able to see all of the signatures and the paging IO, then you know that you've done your page fault handler correctly. Okay, once you're done with that, now you have to implement the destructor and unmap. So unmap, let's go to unmap first. What should unmap do? You can check out here. For unmap, you want to sync any dirty pages. So sync dirty pages just means flush the dirty pages. So you can call flush. We haven't implemented flush yet, but you can call flush. But the most important part is to remove the mapping created by map. Okay, so inside of like every time you called map, you added something to the page map. So what you need to do when you call unmap is you have to remove all the mappings. But remember, you're not clearing the whole page map. You're just removing the entries for this particular MCryptFile. Inside the page map, there are mappings for a bunch of different MCryptFiles. You only want to remove the ones for your MCryptFile. How do you figure that out? Well, you can't read the page table. So that's why you need that supplemental page table, which will tell you what virtual pages are mapped to physical pages and which MCryptFile each line is. So you can just go through them and check which ones are yours. And remember to clear them from both the page map using the unmap function for VM region, and also to clear it from the supplemental page table. All right, so that's the unmap function. For the destructor, destructor is pretty similar. In fact, the destructor is literally just the unmap function. Okay, just call the unmap function. Once you implement that, then you successfully cleared the mappings when the MCryptFile goes out of scope in the destructor. So if you run that, then your retest should now pass, okay, right? Because you're successfully clearing the physical pages and you're removing them from the page map. So then the retest will pass. Then for step 4, then you implement flush. Okay, right now, if you try to run all the tests, the write tests won't pass, because when you call the destructor, what should happen is all of the pages that were written to needs to be flushed out back to the file. We haven't implemented flush yet, so the write tests won't pass. Now is where you can implement flush. And flush is very similar to unmap, I think. Right? For unmap, you had to flush everything, and then you go through and you remove all the mappings. For flush, you sort of go through all the mappings and you determine which ones were written to. Okay, for now, because we haven't been able to determine which ones are dirty and which ones are not dirty. Currently, we're just setting all the protections to be both read and write. Okay, so for now, what you should do is you should just go through the file and just look at everything that is mfile1 and flush them all. Okay, so yeah, if we called mfile1.flush, then you just go through the supplemental page table. All mappings that are mapped to all virtual mappings to physical mappings that belong to mfile1 should be flushed. Okay, so you'll definitely need to loop over your supplemental page table. And once you do that, all of your tests should pass. Okay, which is awesome, right? All the tests pass, finally. Yeah, but remember, just because all the tests pass doesn't mean you're done. There is still 2 more steps that you need to do. I'll go over these 2 steps in the next video. Before we finish, just wanted to talk about a hint for flush. You'll probably be looping over an unordered map. You have some unordered map. Let's say your an std unordered map. And let's say its type is A and B. I'll let you figure out what A and B are. Okay, if you wanted to loop over an unordered map, how do you do that? So it's a little bit different from 106b. In 106b, you would just do something like this. You would do for, I guess, type A, const A key in supplemental page now. Right? And then you would get the values. So you would get the value is equal to supplemental map. You would write syntax like this. And I guess you can, yeah, this is not super efficient because you're going through the map, but then you're trying to access each one again. So in the STL library, this is how you can get both the key and the value. You do something like this. Auto key value colon supplemental. Okay, so this, if you code it in Python, this should remind you of Python syntax, right? This is similar to the Python syntax. Like for key value in supplemental item. Okay, where when you do the for loop, you get both the key and the value. So this is the way that you do it in C++. This syntax here is called a structured binding. It's what C++ stole from Python, and it makes it much easier to use maps. Yeah, this is in C++ 17. Yeah, so this is how you loop over a map. Now, for unmap, you do need to loop over the map, like this table, but you might also need to remove entries from the table. Okay, and remember from 106b, removing from a map while looping is bad. right? In 106b, you were not allowed to do the for loop, and then inside the for loop, you are removing entries as you are looping through the map. So it turns out in C++, you can actually do that, but the syntax is a little tricky. So let me show you what the syntax is. Here you can't use unfortunately, you can't use the for each loop. The for each loop is really nice, but this makes it difficult to modify entries in your supplemental page map. Okay, so instead, what you can do is you can do something like this. And here we're going to use the iterator form of the for loop, which looks like this: auto iter from supplemental page map.in. Kind of just a regular for loop, except we're talking about iterators. Iter is not equal to supplemental. And normally what you do here is you do a plus plus iter. And here's how you would usually loop through the map. You would do key auto key is equal to, you might need a const auto actually. Const auto key is equal to iter first, or rather actually you can just do this is equal to. Don't remember if you need a const here. I think you might need a const here. But anyways, yeah, here's how you would, here's the iterator form. This is equivalent to this for each loop. Okay, but the nice thing about this is you have access to this iterator. So once you do this access, you can choose something like, if you want to remove this key value pair, then there's this thing you can do, which is to do, what's the syntax? It's iter is equal to supplemental page map dot erase. So if you want to remove it, else you move the plus plus iter down here. Okay, so this is the syntax for how do you loop over a map, and then based on some condition, remove that entry. Otherwise, just increment the iter. Okay, yeah, so this is a very common C++ idiom. Yeah, this is a very common C++ idiom where you're going to loop through the map and remove stuff from the map simultaneously. The reason you want to do this iter is equal to supplemental page map dot erase is after erase is done, that entry is gone, but then the iterator, this iterator that is returned is the iterator that points to the next key value pair. So in that case, you don't want to increment the iterator. You just want to use that new key value pair in the next iteration. But if you don't remove it, then you do have to do the plus plus iter. Okay, so this is a tricky unordered map idiom that you use in C++. So yeah, just use this idiom to, if you need to loop through a map while removing entries based on some condition. Okay, I don't 100% remember if you need a const here. You might need a const here, in which case, yeah, I don't quite remember. Maybe you do, maybe you don't. Yeah, if you get a syntax error, then you can also just do this auto key iter first, and then auto to iter. Okay, this gives you the key and the value. Yeah, the reason I'm a little concerned about the key is because you're not allowed to change the key while you do a loop. So I think you need to use this syntax. Okay, and for here, yeah, you probably want to use that syntax too. Okay, if you don't need to modify the value, then you can just use const auto. Okay, so that's it for the map and unmap. I've given a bunch of hints about how you would implement these. So good luck with this part. And we've done all the way up to step 4. In step 5 and 6, you'll go over the page protections and how to make it more efficient. These are not covered by the test cases, but it's important that you implement these because these are important for efficiency reasons. All right, otherwise have a great well, have a great rest of your day while you try to work this, and see you in the third video. Bye.